The centenary lecture on AKR will be delivered by Professor Sayan. Most of you know that he is in the Department of Physics, IIT Kharagpur, and he will deliver the centenary lecture today. And I invite Professor Sayan to come here and deliver his lecture.
Okay, thank you, Professor Banerjee, and also Naresh. Let me also thank, can I have this light, either keep the lights on, or this is just falling on my eyes. The organizers for inviting me to give this lecture. So day before yesterday, in fact, Golam called me and asked for a title. And then I said, there is no title as such. And then I thought a little bit and I looked up some papers. And long back I remember that there was a paper where this phrase was used, and that's in quotes. So I'll tell you about which paper is it later on. And it actually used the phrase the Raychaudhuri effect. And this phrase, of course, has a dual meaning in the sense that, of course, there is the Raychaudhuri effect. We all know about it, and we will come to know in this talk in more detail about it. But in general, there is a Raychaudhuri effect on generations of students, particularly our generation as well as the past generation, who have been influenced not just by his work but also by his personality, by his teaching, by the way he conducted himself, the way he lived. So that is also the Raychaudhuri effect. And that is why I thought that I should give this as the title, because it carries a broader meaning. Okay, so as all of you know, this year is AKR's birth centenary. It's 100 years since he was born. And this talk is going to is entirely based on whatever his work is about, as well as details about certain things, certain other aspects which have come up over the years. So what I'll do is I will first try to tell you about his life and work in brief. And this is going to be mostly from a set of diaries which are in Bengali. So those of you who know Bengali can take a look at this book, which is published by his daughter, Parangoma Sen. So I will take certain things from that diary and tell you about it. And there is also, let me also tell you that there is a very nice biography of AKR by Jayant Narlikar, which was published by INSA, most likely. This is very informative and very nicely written. So if you want to know more details about AKR, you can take a look at this biography. And I should also mention that Professor Narlikar is one person who actually knew AKR right from the early 1960s and knew his work in great detail, and also worked on the Raychaudhuri equation at that time. Okay, so let me move on and let me tell you about AKR's life in brief. So he was born in a place called Borishal which is now in Bangladesh, on September 14, 1923. There are many famous daughters and sons who are from Borishal and who have made a mark in various fields of the arts and sciences, and he is of course one of them. So he had his school education at Brojomohan Vidyalaya, which is in Borishal, which was in Borishal, and he spent a short time there, and then his family moved on to Calcutta, and he studied in Tirthopati Institution and Hindu School, Calcutta, for his schooling. He doesn't write much about his school days in his diaries. He doesn't talk much about any particular influence as such in his school days, except that he mentions his father, who was a mathematics teacher, and he does mention the influence of his father. And of course, he mentions the influence of the school teacher in mathematics and the principal of the school over an incident which I will not get into. You can read about it. And possibly there was some indirect influence because his father's cousin, Professor Hemchandra Raychaudhuri, was very famous, and he was Carmichael Professor of History in Calcutta University. So this is a guess, and this is something which is basically written by Professor Narlikar, so I just thought I'll mention it over here. And there were two brothers of his mother who had brilliant careers in law and medicine. He writes in detail about a bout of malignant malaria which he had when he was a child. He was seriously ill for a while because of that. And there is an interesting incident which is mentioned around that about a certain Dr. Hodge, who prescribed, after looking at various test reports, that he had a peculiar heart. So this he writes in detail in that diary, which is interesting to read. So he became okay after a while, and then he was already in Calcutta. And after completing his schooling, he initially thought he would study mathematics. But then he ended up studying physics at Presidency College, and then did his MSc in physics, completed in 1944 at the University of Calcutta. He doesn't specifically mention anyone influencing during his BSc and MSc. He just says that he studied in Presidency College for his BSc. He was a good student, okay, and he did well in the exams and all. So after finishing his studies in 1944, obviously he would look for a job. And he landed up in the Indian Association for the Cultivation of Sciences, Kolkata, in 1944, first as a research scholar, and then he joined a project which was a metal alloy project under Professor Kedareshwar Banerjee. Now, Professor Kedareshwar Banerjee, yeah.
You are getting too close to the edge.
No, I will not. Okay, fine, thank you. So, Professor Kedareshwar Banerjee is a well-known name, and he is a well-known chemist, quite well-known as such, but he was old at that time. And he set up AKR to work on an X-ray tube And AKR writes this, the name of that tube, it's called the demountable Hadding tube. So he was asked to work on this or set up this X-ray tube which had been bought, and he spent a lot of time trying to set it up, and he writes in detail about what he did. So interestingly, first there was a leak and he couldn't get rid of that leak with glue, because he put the glue and in the night the rats ate up the glue. So after that, what he did was he looked at the transformer. That also was replaced, but nothing happened. Then the diffusion pump. He writes about the diffusion pump also. That also was not working. So nothing worked and the tube was not installed. And this was 4 years. So 4 years went by and this was unsuccessful work. So the CSIR people came, and this was a CSIR project. The CSIR people came and they checked what has been done. They said, well, you have done nothing, so the project is discontinued. So he lost his job. He was in a project, so he lost his job. And once again, he was jobless. Professor Kedareshwar Banerjee told him, good work could not be done, so he was very unhappy. But he also told him, and this is what he writes actually. So Kedareshwar Banerjee told him that, I know one day you will do good work. And he also writes, interestingly, that whether Professor Banerjee told him out of sympathy or whether there was any genuine meaning to it, that is not known. But at that time, he really felt well when he heard these words. So in 1949, he joined Ashutosh College in a temporary teaching position. And it is at that time, around that time, that he developed contact with Professor Nikhil Ranjan Sen in Calcutta, N.R. Sen, who was by and large the only person who knew general relativity and had worked on general relativity earlier and was still working. So he started attending and interacting with Professor Nikhil Ranjan Sen and his group, and he started attending the weekly seminars of this group. But then, while he attended these seminars, he kind of felt that the topics that were discussed were not to his liking. And the approach that was followed was also not to his liking. So he didn't enjoy it. But still he went there for a while and then he stopped. But then he writes that he always maintained a certain degree of respect and gratitude for Professor N.R. Sen. So in the meantime, he was in Ashutosh College, and there was a position, again in IACS, there was a position which was advertised, but this time it was a research officer position. And obviously it was in the theoretical physics department of IACS. And there were hardly any applicants, so he got selected. And he joined the theoretical physics department as a research officer in September 1952. And then for 1 year, of course, he was left to work, so he was doing whatever he wanted to do. After 1 year, for job confirmation, he was asked to present his work to the director and the head of the department in IACS. The director was Professor Meghnad Shah, and the head of the department was Professor Devidas Basu. So he presented his work, and He remembers the date because the day he presented it was his birthday. He presented the seminar on 14th September 1953, and he writes this explicitly in the diary. But then in that seminar, this is a 1-hour seminar, nothing was conveyed. It's not written what he presented, but it's most likely that he presented the work which was to be submitted to physical review later on that year. So nobody understood, nothing was conveyed, and instead he was asked to meet Professor Priyodaranjan Rai, who was a chemist, who was a good person as such, and he was told to work on quantum chemistry. He said, you forget about all this relativity that you are doing, you go and work on quantum chemistry. So Professor Priyodaranjan Rai was a nice person. He gave him a lot of books on chemistry. He went back to his home and started reading those books, and he writes that half of it he understood, half of it he didn't understood. So he was in a terrible state of mind, but still he tried. And that time he read up a paper by Coulson, and this was on network approximation in metals. So he read that paper in its entirety, and then he found out that there were certain things he could actually work out related to that paper, which he did, and then he published a paper on Coulson's work, and this also comes out in 1955. So this paper is acknowledged and appreciated by Coulson in a later paper, and Professor Priyodaranjan Rai is also very happy. And as Naresh told us, the Raychaudhuri equation paper, which we are all familiar with, was received on December 28, 1953 and published on May 15, 1955. So before this 1955 paper, he wrote 2 short comments in PhysRev and Bulletin of Calcutta Mathematical Society, and 3 full papers in Right Shift and in PhysRev. And this paper in Bulletin on CMS was communicated by Professor N.R. Sen. There's an interesting statement about what N.R. Sen told him when he submitted this paper to Professor Sen to take a look. So the conversation, as he writes, says that Professor N.R. Sen made a lot of remarks on the paper, cut out various parts, and told him, and I should say this in Bengali, forgive me, "Joto beshi likhbe tato bhul likhbe." Okay. So this he writes jokingly in his diaries. Translation is, the more you write, the more wrong things you write. Okay. So this was around 1955, and in 1957, that is after the publication of this paper, he receives a letter from, as Naresh told us, Ratnal Brahmachari, who was incidentally S.N. Bose's student and later on became a famous expert on tigers as such. So he informed him about the presentation discussion of his 1955 paper by Otto Heckmann and Engelbert Schuking. Engelbert Schuking is just about 3 years younger than AKR. Otto Heckmann is a senior person, and they discussed it in what was known as Pascual Jordan's seminars in Hamburg. So this kind of encouraged him, and he wrote up a DSc thesis, which he submitted to Calcutta University, and in 1961, the DSc thesis is accepted. John Archibald Wheeler was the examiner, who was very appreciative of the work, and Naresh told you that story. But after that, Professor Kedareshwar Banerjee, looking at the DSC report, proposes his promotion to the IICS faculty. So he said, and AKR writes that Kedareshwar Banerjee told him, Amol, you have done very good work, so now you should get a promotion. So he proposes. But the IICS faculty entirely opposes his promotion and it is denied. So he leaves. Fortunately, he had a DSc, so he had applied to other places. So in 1961, he leaves IICS and joins Presidency College, where he gets a job. And he continues there till 1988. And all of you know, he was a renowned teacher, inspiring generations of students of Presidency and also elsewhere. And post-retirement, he was associated with the Relativity and Cosmology Center, Jadavpur University, as Professor Rashid Banerjee told us. He was also honorary fellow IUCAA, and he passed away on June 18, 2005. So that is a brief recounting of his life as such. Let me now move on to his work. What did he do? What research did he do in his career as such? So here's a list of his papers which I'll show you because it might be stressful for you to look at this, but still take a look. So the red marked ones are the papers which are on relativity but not on cosmology. The deep red papers are essentially the two famous papers, and the light blue papers are in chemistry, and the dark blue paper is in Einstein-Maxwell theory. So if you look at the 5 papers before this 1955 paper, and if you read them, you will find this, the first one is a half-page paper, very short, but there is one sentence there. Negative mass Schwarzschild solution. Nobody thought about it earlier. If you go to the next, the third paper, for instance, this paper I could not extract actually, I didn't get it. The third paper is on structure formation. At a time when there was very little work on structure formation. The fourth paper is in German. This rederives Vaidya's solution. So he was aware of the work that was going on in India, and this is a fact which exists throughout his career. Then this fifth paper is on the Einstein cluster. And then you again have perturbed cosmological models and various other papers on cosmology. You see, this year is 1951 and this is 1961. This is the first 10 years. There are 15 papers, and it is all the papers are written by him alone. Remarkable. He didn't have a godfather, he didn't have a supervisor, nobody. But he worked on chemistry also. He worked on electronic structure. In fact, this electronic energy bands paper is very nice. You can take a look at it. Then he comes to Presidency College. This is in 1962. And here's the paper. The first paper over here is also quite famous. This is what is known as the Raychaudhuri spacetime. Okay. After this, he worked with Professor Sriranjan Banerjee on creation of matter. Then there is a whole set of papers on Einstein-Maxwell theory. Suddenly there is a one-page paper where he talks about space-like geodesics, tachyons and gravitation. And then Einstein-Cartan theory. Then once again you find Maxwell theory coupled to alternative theories of gravity, something in astrophysics called Ferraro's theorem, okay, and conformal flatness and the Schwarzschild interior solution. And if you note his papers, you will see they are not very long papers, very short, all of them. The first paper is 3.5 pages, 1955 Raychaudhuri equation paper is just 3.5 pages. So all these papers are very short, very precise, very clearly written. I have read some of them, so I know. And the other area where he worked extensively is Einstein-Maxwell theory. Okay? But later on, he also worked on domain walls, he worked on inflation, he worked on cosmic strings, and then he came back right at the end to singularities once again. So he has 49 papers in all. So you would say today, by today's measures, that is nothing. So you would say he had done nothing. But I will show you later on what the Raychaudhuri equation is doing. How is it faring as the days go by? He wrote some books, and the book on cosmology is Theoretical Cosmology, Classical Mechanics. These two are course of lectures. There is a Bengali book on mechanics, and these two are basically proceedings. Okay. So broad areas, as I said, relativistic cosmology, including particularly singularities, Einstein-Maxwell theory, alternate theories, domain walls, cosmic strings, general results in GR astrophysics, and 3 papers on solid state and quantum chemistry. So that's the spectrum over which he worked. Okay. So PhD students and collaborators. So today I should mention names of his students. So he would have 13 in all. And this is the list. There were 2 students who got DSc under him. There was one postdoc, Bijon Vakti. Professor Ashit Banerjee is already here. And these are the rest of the students. The only faculty who has the distinction of writing a paper with him is Naresh in 1999. So let me now begin a discussion which will be a little bit mathematical, and this is on the Raychaudhuri equation. So let me first show you where the term was first used, and this is the paper. Otto Heckmann and Engelbert Schucking in this book. This is where they wrote an important theorem for arbitrary models with incoherent matter has been discovered by A.K. Raychaudhuri in 1955. It rests on the Raychaudhuri equation for the scalar of expansion. So this is where it was first mentioned as the Raychaudhuri equation. Okay, so what is the Raychaudhuri equation? And I will tell you the original Raychaudhuri way and then the other way, which is largely due to Raychaudhuri as well as Jürgen Ellert's. So this has been nightly retold by Edward Witten in this Reviews of Modern Physics article in 2020. So you can take a look. So you have d equal to d plus 1 dimensions, space-time M with an initial value surface, S with local coordinates like this. The time-like geodesics are orthogonal to S, coordinate system in the neighborhood of S, and if you have a point P on a time-like geodesic, then that meets S orthogonally at X. And the proper time from S to P is T, then you can assign P coordinates Tx or T minus X, minus Tx, depending on whether you are in the future or in the past. So you take a line element, and this is a special case. Raychaudhuri did a more general case, and which is not very difficult to do that general case also. So this is the line element over here, and you can see that the T geodesic equation is solved for t equal to tau and xi equal to constant. Then what you do is you calculate RTT, which is given by this for that metric. And then you write this RTT in this fashion. And you define V as square root of det G and theta as V dot by V, which is equal to this. And you define a traceless part of G inverse G dot. So, G inverse G dot is a matrix. So, you take this and you define the sigma ij, you define the T mu nu hat and put them in RTT equal to 8 pi G Tt hat. Okay. If you do all this, then you end up with this equation, which is the Raychaudhuri equation. So, the starting point is RTT, as Naresh told us right at the beginning. RTT, and it's called in the paper, he writes it's the decomposition of R44. In those days, there was a fourth coordinate, time was called the fourth coordinate. So, this decomposition of R44 is what leads to the Raychaudhuri equation, and if you have an off diagonal term in the metric G0I, then you will get a rotation and you will get the rotation term in the Raychaudhuri equation. So, but this is quite remarkable. Noticing this fact and then traveling through this and arriving at an equation like this is quite remarkable. Okay, so what is the other more general route, which is there in the 1957 paper, where, and of course later on by Jürgen Ehlers. So, there you take a curved space time, Riemannian or pseudo Riemannian or Lorentzian, you have geodesics and you look at congruences, and you have a congruence definition through each point in a region in space time, one and only one curve passes. And when breakdown of this definition occurs, then these curves meet, that is, they pass through, and if the curves are geodesics, then you have geodesic congruences and you take time like curves. So, with that, and that's a picture of the congruence, you write your trajectory equation, Aj equal to 0 is geodesic, and then you look at this quantity, del j ui. What is that? That is the gradient of the velocity field. That is the crucial thing. So, you take the gradient of the velocity field and look at its evolution, and you remember the non-commutativity of the second covariant derivative, which gives you the Riemann tensor. So, you use this fact over here, and from here just turn this around and use the fact that you are in free fall, and you will get this equation for Bij. Remember, Bij is the gradient of the velocity field. So, if you have a normalized ui, then uj Bij is equal to 0. You define a projection tensor which is orthogonal to ui, and then you define a split of the Bij, which is a split into the symmetric traceless part, the antisymmetric part and the trace part. And then you go back to your equation for Bij, you rewrite this and extract out the trace. So, if you extract out the trace, you will get this equation, which is essentially the Raychaudhuri equation with the acceleration term. This is what is called the acceleration term, del k. So, this is another route, and what I would like to emphasize is that if you look at this equation, Raychaudhuri actually started from the right hand side of the equation, whereas the other approach starts from the left hand side of this equation. So, these are completely distinct approaches to the problem, although they address the same issue, but the approaches are indeed different, and we must realize it is not that Raychaudhuri's original approach has been pursued much, but there is a huge degree of originality in that approach as well. Okay. So, sometimes people refer to Raychaudhuri equations also, and there they talk about the equation for omega ij as well as sigma ij. So, there are equations, as I said, there was this quantity bij, but you have an equation for sigma ij, you can have an equation for omega ij. That is the shear, the rotation and the expansion. So, there is a special property of the omega ij equation. If omega ij equal to 0 is the solution of this equation, which is not true for sigma ij. And that is a picture of what is expansion, what is shear and what is rotation. And in this derivation, you must realize that there is no general relativity. Okay. The Raychaudhuri equations are actually broader in scope and generality, and they are identities, they are always true. Of course, they are used in GR, and we will see how, but one must understand that the Raychaudhuri identities will exist even if there is no theory of gravity. It is that status which is important today. Forget about any theory of gravity, it will be there and it has to be there, irrespective of whether there is a theory of gravity or not. Because the statement is, wherever there will be a vector field, there will be a Raychaudhuri identity. So, in a broader sense, this is actually a generalization of Newton's laws when applied to a collection of particles. Think about it, that is what exactly it is. Okay, so now let me go back to the title of this talk. The Raychaudhuri effect. Where did it appear? It appeared in the 1970 paper of Hawking and Penrose, and this is the sentence: the fact that they do, what they do is basically the existence of conjugate points. The fact that they do is essentially a consequence of the Raychaudhuri effect. So, what is the Raychaudhuri effect? Let us see quickly. The Raychaudhuri effect is this. This is the statement of what is known more popularly as the focusing theorem. So, let us call it the Raychaudhuri effect in future. So, that is my appeal today to all of you. The focusing theorem is there in the paper of Raychaudhuri. Somehow this phrase does not catch, but the equation one was taken by others. So, there are two approaches to this statement of the focusing theorem. It says that if the time-like convergence condition, that is this, holds and omega square is equal to 0, then initially converging geodesics must focus within a finite value of the affine parameter, and this is exactly what is there in Raychaudhuri's paper. And there are various approaches to this proof. You can integrate the inequality assuming convergence conditions, or you can go to the second ordered equation. This is fairly standard and a lot of you would know about it. So, you take this, you assume this to hold good, and you write down this d theta d tau plus 1/3 theta square less than equal to 0, integrate this and arrive at this expression. And you can see that the shaded region in this curve, plot this equality. The shaded region is where the values of 1/theta will lie, provided we start off at tau naught at minus mod theta naught. This is 1/theta versus tau. Thus, it is clear that theta may tend to negative infinity within a finite value of the affine parameter. So, if you start from a negative theta, you will hit the axis. And when you hit the axis, you go to theta going to minus infinity. That is the focusing theorem, and that is the Raychaudhuri effect. So, a converging congruence will eventually focus within a finite value of the parameter, and this is geodesic focusing. If theta starts out at tau equal to tau naught, then it will diverge to minus infinity at this value. Now, Frank Tipler in 1978 wrote a very nice paper where he showed that you could convert this equation to a second order linear differential equation, and if you look for zeros of f, then you can actually rederive the focusing theorem. So, this condition which is important is called the time-like convergence condition, and if you use, now this is where Einstein field equations come in. So, if you replace the Rij with the matter stress energy, then you end up with what are known as the energy conditions, the strong energy condition, the dominant energy condition, the null energy condition, and so on. And all these energy conditions essentially mean one thing. They mean that the energy density is positive, definite in all frames of reference. So, in other words, the cause for geodesic focusing is just the attractive nature of the gravitational force, nothing else. It's as simple as that. In the context of gravity, it's because gravity attracts, geodesics focus if they are initially converging. The null generalization was obtained by Rainer Sachs in 1961, and you can also find the null generalization using the same way as Raychaudhuri did it. You take RUU, decompose it, you will get the null generalization of Raychaudhuri's equation. So, focusing, as I said, and as Hawking and Penrose said, that is the Raychaudhuri effect. So, let us also call it the Raychaudhuri effect henceforth. Okay, what is the singularity theorem? There is something called the Raychaudhuri-Komar theorem. Assume lambda equal to 0, perfect fluid, velocity vector u mu is geodesic and irrotational, expansion is positive or negative of an instant of time. The convergence condition, the energy density of the fluid diverges in the finite past along every integral curve of u mu. This is the Raychaudhuri-Komar singularity theorem, and it is there in Raychaudhuri's paper also. There is a nice comment by Jose Sinovilla in his 2014 review of Penrose's singularity theorem. So, he says theorem 1, this is theorem 1, has one virtue that will be lost in the more advanced singularity theorem. What is that virtue? It predicts that the singularity means a divergence of the energy density, and it says where to locate it. The later singularity theorems, despite their intricate mathematics, does not tell you this, cannot tell you this and does not tell you this. Okay. So, that is very important, but apart from that, the 65 Penrose theorem introduces the idea of trapped surfaces, which also is defined using the expansion. So, there also what Raychaudhuri did plays a role. Well, as I said, it is now how many years? 45, 22, 67 years since the equation was discovered, and as I said, this is a fundamental equation, and therefore, it is something which is much more broader than just within the confines of general relativity and gravitation. It is universal and it is ubiquitous. Now, let me show you what people are doing. 4 examples. First, you look at this picture. This picture is from a paper by Michael Berry in 2007. It is called forced tsunami waves. What is happening? You see, I hope you can see there is a undulation here. There is an island, and there is water gushing over that island. And these are the rays coming from a source, water waves, and these rays create a caustic. What is a caustic? Caustic is where the intensity is very large, very high. That is why the caustic is the place where the tsunami happens. What happens in a tsunami? There is a lot of water at a lot of height, right? So, water waves crossing a submerged island, caustic formation was studied using standard higher order stationarity discussed by Michael Berry. Higher order stationarity is the standard way of studying caustics in optics, in fluids and so on. But If you look at this paper, wave focusing by submerged islands at gravitation analogues by these people, they actually use the Raychaudhuri equation to find the caustics. And you can do that. Why? Because it uses the fact that the loci of points where theta diverges to negative infinity defines the caustic. The caustic is the point or the set of points which is the locus where theta goes to minus infinity. And you can find out caustics using the Raychaudhuri equation. And you can find more, because you can find about shear, you can find about rotation and all kinds of things from this. So, this is fluid mechanics, and the Raychaudhuri equation is used, not can be, but it is used now. Good. 2017, covariant kinematics of light in media and a generalized Raychaudhuri equation. What is done here? You take a laser spot and there is a dielectric. What happens to that spot as it moves through the dielectric? What is the shape? How does it change? That is studied. Once again, analysis and tracing of congruences of light through media that may smoothly vary in character between vacuum, positively refracting and negatively refracting. The kinematics are then used to generalize the Raychaudhuri equation and study how the laser spot will move through the dielectric. Optics. Good. This year, September 1962, there was a theorem called the Bishop-Gromov theorem, very well known. It's about the spreading of geodesics in spaces of constant curvature. You see, if there is negative curvature, the spreading rate will be faster. Okay. Now, there is this paper which looks at an enhanced Bishop-Gromov theorem, enhanced Bishop-Gromov bound rather. And this is written by someone who is very famous, Michael Friedman. Michael Friedman is a Fields medalist, famous geometer. It's a very nice paper, and this paper, the enhanced Bishop-Gromov bound now, this proof makes use of the Raychaudhuri equation. So, it is just the opposite of focusing. Here you look at defocusing and the rate of defocusing. Well, 2 weeks ago, gravity from thermodynamics linking the theory of optimal transport to the Raychaudhuri equation in the internal space. This paper has a nice appendix where it says that there is one identity in geometry called the Bochner identity, which is actually related to the Raychaudhuri equation. For omega ij equal to 0 and for normalized velocity fields, the Bochner identity reduces to the Raychaudhuri equation. So, you see, people are working. All over the world, people are still working on the Raychaudhuri equation. And these are just 4 examples, and there are many more. Starting from the first talk in gravitational lensing. What is gravitational lensing? What happens? Expansion, caustic. Gravity and thermodynamics, I already told you. Mechanical systems, numerous examples. Elasticity, formation of cracks. All of these in papers, renormalization group flows, membranes and branes, embedded surfaces, quantum version, quantum corrected Raychaudhuri equation, large bar Raychaudhuri equation, jamming phase transition, and so many other things. All of them relate to the basic fact. So, as I said, this is universal, this is ubiquitous, and this will stay. Let me just point out one more little thing which Raychaudhuri did, which is also quite well known, and this is what is called the Shom-Raychaudhuri spacetime. And this is a class of solutions of the Einstein-Maxwell equations with charged dust, an electrostatic field and axial magnetic with zero net Lorentz force, and that's the metric, one special case with the Weil-Majumdar relation. So this is a very interesting metric. It has closed time-like curves, but no energy condition violation. There is no classical analog of this spacetime. If you read the paper, the last part of the paper tells you how, if you use the same conditions with Maxwell's equations, you will not get a solution. And a lot of people are actually working on the Shom-Raychaudhuri spacetime nowadays, as I see. So this is also one important contribution which can be looked at, which is being looked at. Okay, so that's essentially the summary, and let me show you some photographs at the end. So this is AKR at a young age, this is AKR at an old age. This is AKR with his wife, and this is with his 4 children. This is in USA. This is AKR with Jose Senovilla and Naresh. ICGC 95. And this is AKR with another great, Professor Shyamol Sengupta in Presidency College, the lower figure. And that is, all of us know who drew this wonderful cartoon. Okay, so let me read out the last few lines in his diary. How long will humans remember me or my work? My students may reminisce once in a while. Let us assume that will go on for about 20-30 years. And given the present scenario of the scientific establishment, it is fair to say that perhaps for 10-20 years or so, or say a maximum of 50 years, my work will have a place in scientific discussions. After that, my work will possibly have no relevance or place in science. However, these speculations are, in my view, that's how he ends it, perhaps foolish. So this is from Diary of AKR, published in this book called Atma-Jigyasa o Onnanyo Rachana. Atma-Jigyasa, you know what it means, and there are several other essays in that book. And this is translated from there. So you can see what he felt at that time about his work. But let us hope that we carry on the legacy that he built, that he nurtured in this little 3.5-page paper that changed so many things. So that's it. Thank you. So if you have anybody has any comments, please go ahead, and then we'll conclude briefly. Yes, please. Question, yeah. Is there a
manuscript available of the version which was submitted to AppJ, which was rejected, and what was exactly done in the astrophysics
No,
part?
I don't think so. Is there a manuscript available of that AppJ paper? Not AppJ, I think Zeitschrift for astrophysics. One AppJ earlier, but the
No, not really. I really don't know. Probably not. But I think we should ask his daughter Parangama.
Parangama may know, yeah.
In the book there is a available or not. Yeah.
Yeah, anything, anybody else, any other comment, question, then we'll stop.
I think
It's okay, it's dinner time, so thank you.
We thank Professor Sayan Kaur for his brilliant lecture, some sort of biographical experiences that of Professor Ramul Raychaudhuri, and also the work in various forms, different aspects. So it is a wonderful lecture, and we appreciate very much, all of us. We thank Professor Sayan Kaur for this centenary lecture all the way. Okay. Thanks again to Professor Sayan Kaur.